oh my God, it would be very hard.
Okay.
Here in Sonora, Sonora is a very warm place. It's very hot here.
Very hot. Okay.
Almost 50 degrees.
50? You mean 50?
Yeah.
Oh my God.
Yeah.
Oh, that's too hot.
Extremely hot.
Yeah, extremely hot. Yeah. So I was in Saudi, even I rarely saw 50. In
50.
Saudi.
Yeah. It's because United Kingdom is have a very cool weather.
Yeah.
Yes. When I met Jack in Guanajuato, in the region of the center of Mexico, that's a better weather.
Yeah.
But here we are very close to Arizona, so
Arizona.
Okay. A lot of places of desert.
Okay. Yeah.
Why.
Of course. Yeah. Fine.
Region of the center of Mexico.
Okay. I'm happy to tell you that we are transmitting in YouTube right now, live. Okay. So everything is fine.
Yeah, sounds good.
How can we call you, Doctor?
You can simply call me Dharma.
Dharma, okay.
Dharma.
No, Dharma Raj. Yeah, people used to call me Dharma.
Dharma, okay.
Dharma.
Because your last name is a little difficult.
That's my father's name.
Okay.
But my name is
Gounder.
Gounder, yeah.
The pronunciation, okay.
Yeah. Perian Gounder. And my name is simply like Dharma. Dharmaraj is my full name, and people used to call me Dharma.
Dharma, yeah.
Dharma.
It's like Jack. Jack is Jaharama. I don't remember the full name.
Jairam Krishnan, yeah.
I was learning with him how was the name are composes. It's very for us it's very strange, but it looks fantastic because it's something very special, unique.
Yeah.
Your names. Yeah, in our cases, the last name is in a heritage. No? You can use heritage.
Yes.
But in your case, is unique.
Yeah, like mostly South Indian names are looked like this.
Okay.
Okay, we are going to start in about 2 minutes. Pablo, would you like to make the presentation of Dharma?
Yes, of course.
Okay. In 2 minutes, I'm going to start recording. And everything is fine.
Okay.
Let me check. I think it's moving, right? It's moving, right? Yeah.
Yeah.
Yes.
Okay, fine.
Yes, it's very good. Okay, we can start, Pablo. So.
Really?
Yes. Go ahead. I'm going to start recording in Zoom. In YouTube is recorded already. Okay, go ahead.
Okay. Dharma, Dr. Dharma, thank you so much for attending this invitation. It's a pleasure for us that you are here with us.
Thank you.
I wanna show a little bit presentation, a little introduction. Sorry, for the attenders of the talk.
Okay.
So, Dr. Dharmaraj Periyan-Grounder has a MS and PhD in physics by the Bharathidasan University in India. He was a postdoc fellow in Saudi Arabia at the Department of Physical Science and Engineering, and currently he's a research associate at the National Graphene Institute Department of Physics and Astronomy, and the University of Manchester in the United Kingdom. Dr. Dharma is working in the Professor Andrew Green, in the Professor Andy Green group, who is a Nobel laureate in physics in 2010. Yeah, I'm right.
Yeah, yeah.
So I think this working is so amazing. Research interest of Dr. Dharma are over nanofabrication of 2D materials, molecular transport through atomical thin materials, graphene-semiconductor heterostructure for Schottky junction devices, optical control memory store, and so on.
Yeah.
So thank you so much. And Dr. Dharma,
thank you.
You have the word.
Yeah, thank you. Thank you very much for the nice introduction, Dr. This is Bablu. I'm really delighted to be here in front of you all to deliver a talk on graphene semiconductor heterostructure for Schottky junction devices. I'm Dr. Dharmaraj Periyanekondar from University of Manchester, UK. So today I will be talking about some of my recent, PhD research topic, that is graphene semiconductor heterostructures for Schottky junction device applications. So before going into the topic, let me give some introduction about my research experience. So since I started my research career, so I have been mostly working on the 2D materials, particularly graphene TMDs, and the PhD of work. The PhD thesis involves the fabrication of graphene on silicon carbide, as well as the monolayer graphene by chemical vapor deposition approach. I also work on the TMDs and using CVD and mechanical exfoliation techniques. So I do the characterization of the graphene and all 2D materials using various techniques such as AFM, SEM, Raman, PL, and XPS, in which I used to determine the layer numbers, quality, morphology, and properties. And most importantly, when it comes to the application point of view, I deal with the lithography techniques to use to fabricate the nano devices based on the 2D materials that I fabricated using different approaches. So some of these applications includes diodes, photodetectors, phototransistor, memristors, and photonic snapshot devices. So this is my overall outline of my research experience. So yeah, now let me get into the plan talk. So this would be my planar talk. So first and foremost, I would like to give some small introduction about the graphene, but which you all may aware of graphene, but still I want to share some of my experience that I have gained during my PhD career, because my PhD work is fully based on the graphene-based device applications. So in addition to this, I'm going to discuss with you some of the unusual properties of graphene, which will be really interesting because it's a completely different physics point of view, and then some of the advantage and disadvantage of graphene, particularly when we deal with the applications point of view, and then the synthesis of the graphene, and followed by synthesis of the graphene, I will discuss about the graphene silicon Schottky diodes, that is a metal semiconductor kind of a Schottky junction diodes, and then the utilization of the diodes for a self-aware optoelectronic device applications such as photodetectors and solar cells. And finally, I will conclude my talk. And let me begin with the history of graphene. So as we all well know that graphene is known to us from 2004, when the two scientists from University of Manchester have fabricated the graphene from highly oriented pyrolytic graphite. But the real history of graphene can be traced back to 1900. In particular, the theoretical physicist Pierre Wallace, in 1947, he has already predicted the band structure of the graphene, but there is no experimental evidence about the graphene. But since then, few experimental evidence proofs have come out, but they were mostly observational and did not give any conclusive evidence for the existence of graphene. On the other hand, meanwhile, some other peoples like physicists have thought that graphene could be unstable. Not only graphene, the monolayer of carbon atoms, atomic like thin material, could be unstable. Even it could be isolated, or even it could be produced because they thought that the graphene or cannot withstand even at room temperature. So all the speculations about the one atomic thick material of graphene have come to an end in 2004, when the scientists have exfoliated the graphene from pyrolytic graphite. So it's, just imagine that if you have a piece of a pencil, or if you have a piece of graphite, just do the exfoliation using some Scotch tape. Do you really believe that if you have a one atomic thick graphene sheet which has some peculiar properties? Okay, so it's really very interesting thing. So for this groundbreaking discovery, so the scientists like Andrew Gaiman and Konstantin Novoselov have got a Nobel Prize in Physics 2010. And the Nobel Prize was not only given to the just exfoliation of the graphene, but because of some of the unusual properties of the graphene that we will discuss one by one in this upcoming slides. So first, I welcome you to the graphene world, because it's a very new material that's give a birth to all other kind of 2D materials, starting from molybdenum disulfide, tungsten sulfide, molybdenum selenide, and even hexagonal boronitride, and so many 2D-dimensional materials have come out only after the graphene. So graphene is the mother of most of the 2-dimensional materials. So, and this is the atomic structure of the graphene. This is just one atomic thick carbon lattice, which is bonded with the sp2 carbon atoms. And this is the conical band structure of the graphene, which is very different from unusual, which is very different. That is unusual band structure. Usually, when you take about the other 2-dimensional material or any kind of materials like silicon, gallium arsenide, gallium nitride, or any materials in nature, it has a parabolic band structure. Something like this parabolic band structure, which can be explained using Schrödinger equation in physics point of view. But in graphene, the Schrödinger equation fails to explain the history or the history behind, or the properties behind the band structure of the graphene, because the electrons in graphene behave an unusual way that cannot be explained by this Schrödinger equation. Rather, instead, Dirac equation is usually applied to explain the band structure of the graphene, because this band structure of the graphene is highly linear, that usually be observed only in the relativistic particles such as neutrinos. Okay, and the graphene is zero bandgap semiconductor, or even you can treat it as a semi-metal. Sorry, let me find the marker. I'm sorry. Okay. So graphene is a very zero bandgap semiconductor, and the electrons in graphene behaves like a massless particle, because in physics we have studied the mass of the electron is something like 9.1 in 10 per minus 31 kilogram something. So, but the rest mass of electrons in graphene is 0, because it like behaves as a photons, means light. So the electrons in graphene behaves as a like photons. That's why it's called massless Dirac fermions, because of these unusual properties. So the mobility of the graphene is much higher, that is around even 10 lakh centimeters square per volt per second. So this has never been achieved in any other materials. And of course, there will be a plenty of physics centered around graphene. So we will be seeing some of the few important physics of graphene. To be honest, one should know the quantum electrodynamics to fully understand the physics of the graphene. And here, in my any undergraduate and postgraduate subjects, I have never studied the quantum electrodynamics, but still I will try to explain as much as I can. And so this one, the client tunneling, which is very interesting topic. So this is, in client tunneling, this kind of a tunneling of a particle through a potential barrier that usually observed only in the relativistic phenomena. On the other hand, there are two different types of tunneling. That one is relativistic tunneling and quantum tunneling. So quantum tunneling is the one that what we are studying in our quantum mechanics concepts. In quantum tunneling, so when a particle hits the barrier, then its momentum changes once it comes out of the barrier because of the potential inflation, the perturbation by the barrier. But in relativistic tunneling, so when the particle hits the barrier, it will come out as without changing in its momentum. So electrons in graphene tunnels relativistically without changing in momentum, whilst this is the quantum tunneling that is applicable for other materials, but this is for graphene, it's completely different. So the probability in quantum tunneling is always between 0 and 1, but here in graphene, it's always 1. So this is because of the pseudospin rotation. The pseudospin is nothing but it's a kind of a different spin that not normal spin 1/2 particle. It's associated with the wave vector that changes with respect to then it's actually a quantum electrodynamics concept, so that can be explained as in quantum electrodynamics. So because of the pseudospin rotation, and the relativistic tunneling, the electrons in graphene have exhibit a ballistic conductivity even up to 65 microns. So ballistic conductivity is nothing but, so when the mean free path of the electrons is higher than the dimension of the material, then you will achieve the ballistic conductivity. Because of relativistic tunneling, that means there is no barrier to stop the flow of electrons. So the electrons can go very fast throughout the crystal of the graphene lattice, even up to 65. I think now it has been more than 65 microns. So, and it's really an interesting phenomenon. And the other one is the unconventional quantum Hall effect, which is also a relativistic counterpart of a quantum Hall effect. And other particular important thing is the electric field effect. That means you can tune the carrier concentration of the graphene from low to high or electrons to holes by just applying or by just changing the gate voltage. And the other thing is that quantum broadband absorption and carrier multiplication phenomena, because these are the important facts that usually applicable in the photonics-based applications. And graphene has very high electric current carrying capacity around 10⁸ ohms per centimeter squared. And moreover, graphene is very, very stronger than steel and has high thermal conductivity and high stability. And yeah, it's very strong material that have ever discovered in nature. So far we have seen some peculiar properties of the graphene, and but graphene is still not an ideal candidate for certain applications. For example, let me give you a better examples. If you take some like radio frequency based applications, graphene is the best candidates that we have ever produced. Okay, for example, graphene based transistor have exhibits like more than 100 gigahertz, 500 gigahertz frequencies where we don't bother about the band gap. But when it comes to a band gap, particularly a field effect transistor where we need to switch on and off the devices, then graphene is not an ideal candidate because of its zero band gap. But still, you can achieve with graphene by coupling the double dual gate structure or making a bilayer graphene by introducing some band gap. But those techniques, requires very high advantage techniques, mostly clean room based techniques, which involves a lot of very expensive techniques. But if you want to fabricate some easy and low cost and devices with graphene, then you of course ultimately need to look for an alternative devices. And as we discussed before, graphene has high current density, which means if you have very high current density, then you will have always high off current. So then there is no on, so the switching speed will be very, very low. And moreover, the other thing is that the ultra fast photoluminescence. So this phenomenon is in fact a disadvantage of graphene because graphene lacks a band gap. So when you excite the electrons in graphene with light, then what happens? Because of zero band gap, the electrons on hole will easily recombine and gives rise to no photocurrent. So gives no photocurrent at all. So there won't be a no photocurrent generation with graphene only devices. But these can be improved with different kind of structure. But as I mentioned before, those are complicated and requires sophisticated facilities and mostly clean room facilities, and it requires very higher advantage facilities. So the above mentioned drawbacks of the graphene can be overcome by just coupling the graphene with some suitable semiconducting materials such as silicon. Because when you couple graphene with silicon, then you will get the benefit of the graphene as well as the benefit of the silicons or any semiconductor, as well as the benefit from the interface between the graphene and hello, can you hear me?
Yes.
Yeah, okay, good. Yeah, so these kind of graphene semiconductor heterostructures will behave as a standalone devices and act as a basic building block for any electronic and optoelectronic systems. In fact, this is the best candidate for solar cells, photodetectors, and photodetectors. So the advantage, I mean, here I would like to point out why I choose silicon instead of other semiconductors, because silicon is the mostly widely used semiconductor in electronics and optoelectronic industries with an indirect bandgap of 1.1 electron volt and high mobility for both electron and holes. So I want to couple graphene with the silicon so to make a Schottky junction devices. So for photodetectors, that is optoelectronic device applications. So because it's very highly compatible and easy to integrate. And before going into the next topic, so I would like to give some important introduction about the metal semiconductor junctions. So because here you can consider graphene and silicon as a metal and semiconductor, because the metal and semiconductor is an important and key component in electronic devices, and in fact that determines the characters of any not only electronic devices such as FET, MOSFET, and MOSFET, but also optoelectronic devices such as even including photodetectors and even solar cells. So this metal semiconductor contact are very, very important. And in particularly if you take the metal oxide semiconductor devices, you will always have like source, drain, gate, and channel. The channel should be a semiconductor, source, gate, and drain should be a metal. So here always there is a metal semiconductor, and here metal and semiconductor. But in metal oxide semiconductor field effect transistor, you need to have a barrier, that is barrier to separate the channel. In field effect transistor, the gate should always be separated from the channel so that the gate can easily modulate the carriers in the channel material. The channel should usually be a semiconductor that may be either N-type or P-type, that doesn't matter. But when it comes to the metal semiconductor field effect transistor, and you don't need to have a barrier here, because this metal and the Schottky barrier between the metal and semiconductor will play the role of the barrier oxides. So why here it's important is because, you know, when you couple the metal and semiconductor, it may be either ohmic or Schottky. So when you couple the metal with semiconductor, it may be either ohmic or Schottky. The important thing is that in any electronic devices like MOSFET devices, the source and the drain must form an ohmic contact with the semiconductor channel, while the gate should form a Schottky barrier. So if you use the same material, like for example, if you use the same material like source material, then you should have a barrier material here. And so by appropriately choosing the metals with appropriate work function as mentioned in this criteria, so you will achieve whether ohmic contact or Schottky contact. So in any electronic devices, there are two contacts, one is ohmic and one is Schottky. So ohmic contact is mandatory for transporting the electrons without any barrier, while the Schottky barrier will determine you are the and the resistive, I mean, the rectification behavior or switching characteristics. In fact, the Schottky diode is almost equal to the PN junction diode, because in PN junction diode, there you will see a barrier between the P and junction. In Schottky diode, so Schottky means nothing but the metal semiconductor. But please don't confuse here. The metal semiconductor can be ohmic or Schottky, but I mostly use the Schottky to mention metal semiconductor. Okay, so I don't talk much about the ohmic. So in this devices, so just wherever you see the Schottky diode, just consider about this criteria and just assume that this is a Schottky diode with rectifying characteristics. And then, okay, so with this introduction, so let me go to the synthesis of graphene. So this is the general common techniques that's involved in the fabrication of the graphene. So not only graphene, most of the 2D materials like MOS2s, TMDs, even hexagonal boron nitride, and there are several methods like mechanical exfoliation, CVDs, chemical engineerings, and epitaxial graphene on silicon carbide and liquid phase method. But mostly most advanced methods are chemical vapor deposition methods, because it can produce a very large scale 2D materials irrespective of the other, without changing in any qualities and properties. So it can give you the better quality as well as the better area of 2D materials. So I also chose chemical vapor deposition for my growth of graphene. So this is a schematic diagram of the chemical vapor deposition chamber in my PhD laboratory in India, and I used acetylene as a carbon source for the growth of graphene. And so when the acetylene is introduced into the chamber at 970 degrees Celsius, the copper is act as substrate for the growth of graphene. Of course, in the copper, in fact, act as a catalyst for the growth of graphene. A metal catalyst is always needed to induce the growth of the carbon-based material. So I choose copper. Most people usually choose copper because it has a very low carbon solubility that results in the monolayer growth of graphene. So what happens when you flow acetylene and you heat it up to 970, close to 1000 degrees Celsius? This acetylene can be decomposed into carbon and nitrogen, and the decomposed carbon will segregate and form as a graphene layer. So the layer numbers can be controlled by using some different parameters such as the growth time and acetylene precursor flow rate, time, and the cooling rate. So there are many facts that determines the control number layer, layer control over the process. So here I have grown the graphene on copper substrate. Of course, copper is a metal. Graphene is almost like a semi-metal or metal. So I don't need the graphene in my case, because I need to transfer into semiconducting substrate or semi-insulating substrate for my device applications. So I need to etch the copper underlying the graphene. And this is actually a standard process for the graphene transfer wet graphene based wet transfer approach that involves the PMMA coating. So the PMMA will strongly hold your graphene when you bake it at 180 degrees Celsius, and the copper underlying the graphene can be etched using ammonium chloride, ferric chloride solutions. And once this copper is etched, the PMMA with graphene can be transferred onto the desired substrate like silicon dioxide or silicon, and then after that, then the PMMA will be removed using acetone. So after I transferred the graphene, I characterized the graphene using Raman spectroscopy, and the SEM Raman spectroscopy reveals the formation of the monolayer graphene, but SEM also reveals the monolayer graphene, but unfortunately there are a lot of PMM residues. But in the later, I completely reduce the residues, but unfortunately I don't have the image to provide you. I'm sorry about that. So after the device fabrication, after the graphene growth and characterization, so I have fabricated a field effect transistor. So for field effect transistor, this is the schematic diagram of my field effect transistor, which involves source, drain, and gate. This is not a Schottky transistor, Schottky diode-based device. This is just a field effect transistor, which always needs to be on an oxide materials, that is a dielectric material, that is silicon dioxide. This is the optical image of the devices. And so when you apply the gate voltage, the carrier concentration in the graphene can be modulated, because the gate can able to modulate the Fermi level of the graphene that results in the change in the conductivity, change in the current value. So when you change the graphene from, gate voltage from negative to positive side, the conductivity, the electrode transport properties of the graphene is, the current is reduced, and again it start to increase at around 35 voltage. That means this graphene is not an ideal graphene like as a pristine graphene, because it's highly doped. So ideal graphene should have a linear, ambipolar behavior. This is highly doped graphene. So as I mentioned before, the ideal graphene has a Fermi level close to the Dirac point, not below the Dirac point. Here, this confirms that this device results confirm that the Fermi level is close to the conduction band, not at the Dirac point. That means it's a p-type materials. The graphene is p-doped. So in generally, the p-doping in graphene is usually expected in CVD-based approach because it involves like a lot of, a process like PMM residues and water molecules, which may induce an additional doping, that whole doping to the graphene that results in the shift of the Fermi level to the conduction band. So after my basic studies, then now I fabricated the graphene silicon Schottky junction diode. That means I coupled the graphene with the silicon. So this is the schematic diagram. So in my previous devices, I just transferred the graphene onto the silicon dioxide. But here, to make a metal and semiconductor junction, I just etched the remaining part of the silicon dioxide using HF and transferred the graphene in order to make in contact with the silicon. So now I have my device is like a graphene semiconductor structure. And meanwhile, the ohmic contacts to graphene, it can be found by titanium, gold, and ohmic contacts to silicon can also be found by silver or gold, because in any electronic circuit, ohmic contacts are mandatory. Ohmic contacts are nothing but, for example, if you apply a 10 volt or if you apply a 1 volt, then the ohmic contacts will supply the 1 volt to the graphene system without any change in node, without any changing in its value. For example, if this is a Schottky barrier, if this has some barrier, if this is not ohmic, then if you apply a 1 volt, then the 1 volt will not go to the graphene perfectly. So there is some drop in the voltage at this interface, so you will not get the perfect results. Of course, this should be a Schottky barrier, but the ohmic contact should not be a Schottky. So that's what the point is here. The ohmic contact is then essential in any kind of devices, even though it is Schottky barrier. So once this is the electrical curve for TiAu and graphene, as well as the gold and silicon, but not for graphene and silicon. So here, this is the IV characteristics of graphene and silicon. So it completely reveals the rectification behavior. That means it behaves as a Schottky diode. So, and with the rectification ratio of around, I think, close to 500 or thousands, I forgot the value, but it has a very rectification value. You can see clearly that there is no current under the reverse bias, and the forward bias you can see an increase in the current. That means this is a perfect Schottky diode characteristics. So based on these thermionic emission relations, as well as the dark current value, and I calculated the Schottky barrier height, which is around 0.75 electron volt. So this is the schematic energy band diagram that I derived from this Schottky barrier, as well as this rectification diode behavior. As I mentioned before, my graphene is a p-type, that is the Fermi level is in the valence band, edge of the valence band. And what happens when you combine semiconductor with the metal? So there will be a misalignment between the Fermi levels of the semiconductor and the metal. So in order to make equilibrium, the Fermi levels of the metals will bend and reach the equilibrium with respect to the Fermi level of the metal. So that results in the band bending mechanism that gives rise to the depletion region, as well as the Schottky barrier height. So this is the Schottky barrier height of that I calculated, which yields which also yields a depletion region of around 0.6 electron volt. So this depletion region important, that both the depletion region and the Schottky barrier has a linear relationship, when both determines the rectification ratio or rectification behavior, or in other words, the switching behavior. And particularly when it comes to an optoelectronic point of view, it determines the performance of the devices. So after demonstrating these graphene silicon Schottky diode, I just applied these devices for an optoelectronic devices, that is a photodetector. I just shine the light on the graphene and semiconductor, And here the graphene in fact act as a carrier collecting layer, and because it's very transparent, and also anti-reflection layer. Silicon in fact acts as a photo absorption medium, and the interface between the graphene and silicon, as I mentioned before, the depletion region or built-in field, whatever may be, that will help the device to generate a photocurrent upon the photocurrent separation. So what happens, this is the IV characteristics of the devices with elimination of the different laser power. This is the black one shows the dark current. So when you shine the light, you can clearly see the increase in the photocurrent of the devices. So the devices in fact performs as a photovoltaic devices, that is like a solar cell. This is in fact like act as like a semi-Schottky junction solar cells, which is based on a Schottky barrier based applications, and that is in fact it is a self-powered because it's a photovoltaic. That means you don't need to apply any bias to generate a photocurrent. For example, even at zero bias, it can produce a significant photocurrent. So that is a self-powered. It's like, just imagine is how a solar cell works. So you don't need to apply any current to produce any extra current. You just get it just absorbs the light and will give you the current. So this is the mechanism that I proposed based on the information I provided. So this is the energy band diagram that I have that I discussed before. This is actually after the silicon and after graphene and silicons are in contact. So what happens when you shine the light? So of course it will create an electron hole pair in both in graphene and here. But here, it will easily recombine. So I don't show it up. But this is when you shine the light, it will excite the electrons from the valence band, and it goes to the conduction band by leaving the holes in the valence band. So once these electron and holes pairs are separated, then it will not recombine because there is a depletion region or potential barrier. It will not allow the carrier to recombine. Rather, it will instead it will easily help to transport the carriers towards the electrode sites. So that results in the photocurrent. And so I also calculated the photocurrent and photovoltages based on the for a different laser powers. So in dark, you can clearly see that increase in the photocurrent with respect to the different powers, and the photovoltage for the max is calculated to be around 200 millivolt at the laser power of 5.7 milliwatt per centimeter squared. Of course, these photocurrents can be increased if you go more, if you go beyond this power. And the photocurrents also shows an increased tendency with respect to the increased laser power. That is because when you shine the more photons, then it will give you the more photocurrents. And the other important thing is that power dependent photo switching. And I also checked the continuous behavior, or in other words, the quality of the materials by exposing several cycles for a different laser powers. So all exhibit a clear, perfect switching behaviors for all different laser powers. And the other thing is that the photo responsivity and on-off ratio. The photo responsivity is a figure of merit of a device like optoelectronic devices such as graphene and silicon Schottky diode, which determines the efficiency of your devices. So if you have a very high photo responsivity, then you will these devices can be used in the optoelectronic device application, particularly monolithic based applications. So here the responsivity of the device is found to be 510 milliamps at very low power concentration at zero bias, because the device can produce a responsivity of 510 milliamps even if you don't apply any particular voltage. And this value actually decreases with increasing the voltage because of different mechanisms involved in this process. And in addition to this, you can see another interesting features, that is a photo on-off ratio. On-off ratio is nothing but the difference between the dark current and the light current when you on and off the light. So this is very, very high, around 10 power 5 times, around, like, just imagine that's 1 lakh times the photocurrent is higher than compared to the dark currents. That's really interesting. So this kind of devices with photo on a face, you can be ideal candidate for most optoelectronic devices. So and in addition to this, as I mentioned before, the electrons and holes can produce a photocurrent, but here in this picture, I would like to show you how quickly the generated carrier or the excitons can be dissociated, or converted into the photocurrent. So this is a special setup I have made to analyze these properties. So instead of eliminating the laser photons continuously, I used a chopper to modulate the laser pulses. So I chose to chopper around 20 Hz frequencies, so it can modulate the laser frequencies, and the signals can be collected using digital source oscilloscope from the single standard modulation cycle. So I calculate the response time and recovery time of the devices. Response time is nothing but when you shine the light, so the time taken for how quickly and then the electrons hole pairs are converted into photocurrent. So this is around 130 microseconds. So within the 130 microseconds, the electrons and holes are converted into the photocurrents. That means there is no recombination takes place around this time. And when you shine up the light, then this device will recombine immediately to the ground state. That means the device has of very high quality. So if you have defects, then this will not reach to the ground state very easily. And so this very low recovery and response times are also an ideal candidate for the optoelectronic devices based on the graphene and silicon heterostructures. And besides, the photo stability of the device also tested under self-power conditions. And I just recorded for around 10 minutes. Of course, there is no decay in the photocurrent, even at high power was observed. And that means this device has very good stability, not only in terms of the photocurrent, but also in terms of the performance. So it has very long-term stability and maintains the photocurrents without any changing in its value. And of course, it's thanks to a Schottky barrier that makes the life easy because of the Schottky barrier between the graphene and silicon carbide. So we got some very high responsivity as well as the photo switching and the high response speed. So these are the ultimate candidate for the technological implementation of the devices. So far what we have seen is that, so we have like a graphene, which is not a good for a certain optoelectronic application. So I combined graphene with the silicon and make a Schottky diode. The Schottky diode has a Schottky barrier, and the Schottky barrier has a potential advantage not only in terms of electronic point of view, but also optoelectronics applications. So the optoelectronic applications like photodetectors, so the Schottky barrier associated with the built-in field or diplex region helps to get a more photocurrent, helps to achieve a very good photocurrent with very high stability. So starting from the materials, so we have seen that graphene, we have seen some important properties of the graphene, and then the synthesis of the graphene by CVD, and then graphene silicon as a Schottky diode, and then we demonstrated a cell for photodetectors with a responsivity and very high responsivity and on-off ratio and very response times. So I think I have come to the end of the talk. And I really thank to my PhD supervisor, Professor K. Jagannathan, for giving me an opportunity to work particularly on this topic. And I thank Dr. Jairam Krishnan for referring me to the Dr. Jesus Bablu. And many thanks to Jesus Bablu for inviting me this wonderful talk. And I'm really happy to deliver it. I'm really happy to deliver in front of talk with you all guys. Thank you very much. So just feel free to contact me if you have any questions.
Thank you so much. Thank you so much to Dr. Dharma for this interesting talk. So we open a space for questions.
Yeah.
Okay, thank you so much. So these questions
Any questions?
I have one.
Okay.
Yeah.
What are the advantages? Now we're talking about graphene, but for other hand, we have the borofin. What are the advantages or disadvantages of graphene over borofin? This thing of stuffs.
You mean, I think I don't get your question.
Yeah, the borofin.
Yeah. There's another 2D materials. Yeah.
Yeah, it's another 2D material.
Yeah.
There are some compatible devices that we can make with the borofin, or is completely different. I don't know. I actually don't know.
Yeah. Of course, with any kind of 2D materials, you can make like the same devices, but it depends on the nature of the materials, how it is. For example, if you take a boron nitride, monolayer boron nitride, this is a perfect 2D material, but this is an insulator. This is an insulator, not a metal. Even though it's monolayer, it's an insulator. So that material cannot be applicable to this kind of applications because that's an insulator. So we need to have a metal or semiconductors, so to get some optoelectronic properties. Yeah, I think borofin is recently emerging, and there are a lot of research are being done, and hopefully we will get to know more in future.
So graphene for this kind of junctions you made your study.
Yeah.
Graphene is better.
Yeah, of course, graphene is better because there are several reasons I could say. In case you can use some metals instead of graphene, because that's also metal-semiconductor junction. But the advantage of graphene is that graphene has very high mobility, and it's a monolayer. And for example, if you take like a metal like gold, copper, platinum, or whatever maybe, you cannot make it down to monolayer, right? Or uniform. So you need to at least have a few 10 nanometers or 50 nanometers or 100 nanometers. So when you use those kind of devices in applications, it will completely block the light. It will not allow the light to pass through the silicon. But here graphene is highly transparent. And monolayer thickness, it's completely transparent to all kind of photons. So, and one more thing is that graphene could form a high potential barrier, built-in field with respect to the silicon. That's a better advantage. Yeah. And even a recent report says that graphene silicon solar cell have exhibited an efficiency around 15%. Yeah, that you cannot achieve with any other metals. So graphene has a lot of advantages. But if you want to fabricate graphene only devices, you still can do, but those are complicated. You need to make a dual gate structures, or you need to make like several lithography techniques, and it involves a lot of process. So that's a different techniques, different study. But what I have shown is just simple. It's not a complex technique. It's just a simple technique that anyone can do without any clean room techniques.
Any other question?
Dharma, I have a question. The graphene-based electronics is a revolution, I think. But how far or how close are we of having graphene components in my laptop? How do you say 5 years, 10 years?
Still, I mean, in laboratory scales, people have already made a big achievement. Like even mobiles, so graphene-based mobiles have already come out in especially touch screens or some things. But like a chips-based, then it's still underway. So it's think maybe if I guess correctly, then it may take another 10 years. Not only graphene, there are some other 2D materials which are particularly promising, like MOS2. So the 2D materials-based devices can be expected in future. But there are some disadvantage, like still it's like competing with silicon in many point of view, because silicon is very standard and high quality and easily available. So the other 2D materials we need to have over large scale and need to withstand several approaches, need to have very high quality, but we have got achieved in laboratory scale, and it's in like in industrial scales, though it's like under processing. So hopefully maybe another 10 years, within another 10 years, we can expect some devices based on 2D materials only.
So we are going to see graphene components in a laptop, I expect.
Laptop, okay, you mean it's active component or like monitors or something? So because there are different type of applications. Graphene can be used as a like in chips as well as in the touch screens, like after so it depends. So if you like, for example, because of its high transparency, there are some devices based on graphene have already come out. Even Samsung have produced a graphene based mobile, I mean in touch screens, graphene based mobiles, which shows very good performance. But
okay, so right now we have components based in graphene.
Components,
electronic components with
electronic components. Right now we don't have much in commercial in market. We don't have much available in market.
Okay. Well, in your slide 22, you presented a switch, but I don't know, it's a kind of slow, the switching. I was expecting a faster transition.
Which one? This one?
Yes.
Oh, okay. I think it's a different view. Okay, let me explain you.
Mm-hmm.
This is not that doesn't mean switching. So that's a different concept. So let me explain you. So here, this is the schematic energy band diagram. So what happens when you shine light, the electrons and holes pair will be created. The electrons and holes pair will be created. So generally in semiconductors, so once the electron and hole pair separated, there is a possibility to recombine without contributing to the electrical current. So if it recombines, then it will emit as a photons and there is no photocurrent will be produced. Okay, so that 130 microsecond means within the 130, I mean, the device takes 130 microseconds of times to get converted. I mean, the electron and holes get converted. So within 130 microseconds of times, the electrons and holes are getting converted into a photocurrent. So that doesn't mean switching.
Okay. What is the role of the Dirac point right there?
Sorry, this one? What is that?
Yes.
Pardon?
What is the role of the Dirac point?
No, the Dirac point, actually, this is an energy band diagram. So derived from energy band diagram. So the Dirac point is the point at which the valence band and conduction band meets, where the electrons behaves like a photons.
Yes, because it looks like a transition, a normal transition between bands, but the Dirac point.
This Dirac point is just nothing but the point at which the band span and conduction band meets. But this is not the same criteria for all cases. This is just a schematic. Usually, the band structure should not be like this. This is a schematic. This is a charge. In other words, a charge neutrality points, we can say.
It's like a transition between bands. We have a lot of students, Dharma. I would like to have a question of one student.
Sorry?
I would like to have a question from the students, because we have a lot of students right now.
I don't, pardon? Students?
Students? We have student. You have some students in the assistants. Between the assistants.
Okay. So,
I don't know if one of them want to make some questions.
Feel free to. I'm very happy to answer.
So you can ask in Spanish also.
Spanish?
No, yeah,
okay.
for the students.
Okay.
Yeah. You can ask in Spanish if you want. Si quieren pueden preguntar algo en español para nuestro ponente. Well, I have a simple question.
Yeah.
So to produce graphene layers, you said one of the technique is by CVD in a CVD chamber. Yeah.
Yes.
Is this the best technique, or
This
one
is
of the most?
No, yes, this is the best technique to produce high quality large scale graphene, large scale 2D materials, not only graphene, 2D, all kind of 2D materials, like all the 2D materials. Is the best technique. It's the best approach. Because with the because the Nobel Prize was given to the one fabricated from mechanically exfoliation, right? But still, you know, that disadvantage is that you cannot like produce more than 100, 200 micrometers. But with the CVD approach, you even get like 100 meters, 200 meters by rolling roll to a different approach. So the CVD is the ultimately best way. But the thing is that the quality, of course, it's very good, but may not be good as the mechanically exfoliated one. So each method has its own advantage and disadvantages, but CVD is the best one, as far as I know.
How big is the layer that you can create with CVD technique?
The CVD technique?
Yeah, centimeters, or how big?
Yeah,
is?
of course you can. Of course you can make it in or centimeter scale.
Yeah,
but the layer,
commercially,
the thickness should be 1 atom. There's no doubt. But the area, the size that you can make it like depends on the substrate you choose. For example, if I place the copper like 1 centimeter, then the graphene will go over the copper for 1 centimeter. It depends on how the size, how much size you choose.
Yes. Commercially, is sold by 5 centimeters square. I don't know, something like that. Yeah.
Yeah.
Okay. But the first time that was obtained by Professor Game, it was with the Scotch tape.
Yeah. He produced with the Scotch tape.
And with the graphite of a pencil, or
with the graphite, he just took the graphite and did just exfoliation mechanically, and finally they got like it's a monolayer. But the technique is it's they did something new in terms of technique, but the most important thing is that they found some peculiar properties of the graphene that we have never studied in our school physics or college undergraduate and postgraduate subject. So they brought something new to the world. So that's why they have the Nobel Prize was given to Professor Andrew Game and his student Kotze and Oslo.
Any question? I have another one.
yeah, please, welcome.
So to manipulate graphene, so you need to put it into a layer, in a substrate. So silicon, for example.
So
the layer of graphene need to be on some substrate. Substrate.
Yeah, it should be something like this. You just need to transfer something like this.
Yeah. So you need to
it should be something like this.
Exactly that.
Yeah.
So it's completely necessary to have for example, in this case, a silicon substrate to work with a graphene.
Yeah, the silicon. Yeah, this should be in contact with the graphene. Should be in contact with the graphene.
It's completely transparent. Here, there's are some researchers that work with graphene, but
the graphene is completely transparent. The graphene is completely transparent. In reality, in naked, you rarely see the graphene. But if it's a large scale, you will be able to differentiate. But it's very hard to see in practically if it's like a few micrometer scale. you always need a microscope to confirm the layer number, because yeah, it's a
Okay.
good challenging task.
Okay. Any other questions? Jesus, any other question?
How expensive is to make this device, Dharma?
Sorry, pardon?
How expensive is to make this device?
This kind of devices, you just need a silicon wafer.
Okay.
And you need to have a CVD furnace.
Okay.
To grow graphene.
Is...
And that's it. And to measure the device properties, you need like a semiconducting characterization, like analyzer, like semiconductor characterization, like Keith Lee. I think just you need to apply some voltage and to measure the current. You need a system, something like this.
Okay. I think that this experimental technique we have in Mexico.
You might be having, yeah.
Yes.
And even this device even responds to your room light.
Okay.
Because it just needs photons, so that it will give you currents. Because it has silicon. Because silicon, of course, is a known material for optoelectronic devices.
Dharma, this graphene layer is how thick is this graphene layer? Is monolayer or bilayer?
Yeah, this is monolayer. This is monolayer. Sometimes, yeah, sometimes I even use bilayer also, but not more than bilayer.
Okay. Experimentally, you do the monolayer graphene?
Yeah, experimentally I do, yeah.
Okay.
Experimentally, I did fabricate monolayer graphene by CVD.
Okay.
Also, I did another approach that is the epitaxial graphene on silicon carbide. You know that I haven't discussed here. That's also a part of my PhD work. So that is silicon carbide, right? So that I use the carbon in silicon carbide to convert as a graphene by just annealing the silicon carbide substrate at very high temperature. So that will also give you a monolayer graphene.
Okay. Dharma, it is not clear for me what is the role of the Dirac point in the conduction properties of the graphene. The electric conduction, how is affected by the Dirac point?
Electrical conduction, how it affected by, actually, yeah, the concept is if the Dirac points, if the valence band and conduction band meets at the Dirac points, then the thing is that the properties of the graphene can be tuned from electrons to holes. Okay, the Fermi level of the graphene can be tuned from electron to holes. And most of the peculiar properties, like what we have discussed, massless Dirac fermions and relativistic tunneling, are measured at the Dirac point. So that is actually a point just given to the name Dirac for its unusual conical band structure.
Yes.
That linear band structure.
Yes.
In ideal graphene, pristine graphene, ideal graphene, defect-free graphene, or undoped graphene, the Dirac point and Fermi level is same. If your graphene is doped, like has defect or something, then the doping could shift the Fermi level below or above the Dirac point.
Okay.
So, like all the peculiar properties, like very high mobility, massless Dirac nature, are all like observed at Dirac point, where the Fermi level is.
Dharma, we have the textbooks about the electrical properties of graphene.
Okay.
We have?
Electrical properties of graphene. Yeah, there have been few books. Maybe I can.
Do you remember the name of these books?
I couldn't remember exactly now, but I have it with me. Maybe I will check and give an email to you. Is that okay?
Okay. Okay.
Yeah.
I have a couple of books based on graphene, not only graphene, even for general like 2D materials based devices.
See, because this property are not the normal solid state theory. Is different.
Yeah. The thing is that as I mentioned before, one should need to learn quantum electrodynamics to fully understand the properties of the graphene, because most of the concepts are derived from the quantum electrodynamics.
Okay.
So I also have never studied quantum electrodynamics in a undergraduate and masters. So it's very hard to understand for new students.
Yes, I think it's a lot of theory.
But it's really interesting.
Okay.
Really interesting. So you will learn a lot, and you of course you even don't need to have a textbook. There are a lot of papers published. Maybe I can suggest you some of the papers. For example, the rise of graphene, a new roadmap for graphene. There are a lot of papers you can download and read. It will give you a lot of information about graphene.
Everything started with the Nobel paper some years ago.
Yeah.
And applied the first
paper was published in 2004 December or 2005 January, I don't remember, and in science.
In science.
So in science. So in which they have studied a few layer graphene properties. That is, the title of the paper is Electric Field Effect in Atomically Thin Carbon Flames. But in the same year, they have published some other papers in Nature and several papers with monolayer graphene with some peculiar properties. So after that, everyone starts to work on graphene.
Okay.
So as time goes up, people have changed their materials to another 2D materials like MOS2. So graphene, in fact, indeed gave a birth to all kind of 2D materials.
Okay. And the Nobel Prize become with this paper, the science paper, I think.
Yeah, science paper, and also some of the other papers. But science paper was the major one behind the Nobel Prize.
Okay. Dharma, what is your favorite paper that you have made in this field of graphene?
To be honest, I have not done much on graphene. Okay. Because I'm not a pure physicist, I'm a material scientist. So, and I would say one of my APL paper would be the best.
Okay.
I'm sorry.
Yeah.
How is to work in a Nobel laureate group?
It's a good question, but I don't know how to answer. The thing is that you need to be up to date. You need to be up to date because they are extremely talented. They are extremely, like you need to go. You need to like how to say. You need to go behind them, like because they will move fast. You need to go.
Okay. How many people are working in this particular group?
Because I'm new to this group, I just recently joined in January. I'm very new. I'm like I'm at the new stage, but in Andrew Games group there are few peoples, like I don't know exactly because there are peoples from different
places,
departments,
universities.
not places, universities, different departments within the University of Manchester, because we have Department of Physics and Astronomy, National Graphene Institute, and there are several things, and yeah.
Okay.
doing really good research, and the facilities in the particularly in National Graphene Institute is really good.
Okay. Well, I don't know if there is another question.
Yeah, I have one.
Yeah.
Okay. Thank you so much.
Do you know how were the graphene properties? I'm sorry. How were the graphene properties discovered? Because in nowadays, it is a material that I have heard a lot that has really good properties.
Pardon? You mean hello?
Jenny?
I'm sorry?
Can you? Yeah. Could you please repeat your question?
Yes. Do you know how were the graphene properties were discovered?
Okay. So you
No,
mean how are the properties discovered?
yes, because in nowadays it is a material that I have heard a lot that has a really
Okay.
good properties, but I don't know.
Okay. I got your question. So all the properties are discovered based on the research findings that was conducted in a laboratory. So in my laboratory where I'm working in, so all the discoveries have gone.
Okay.
So people make devices using graphene, and then if you start to analyze the devices, you will observe some peculiar behavior that you have never observed before. So if you get in deep into the device results, then you will get to know the peculiar properties. So this is the way most of, or not only most, all the peculiar properties of the graphene have discovered. I would say for an example, so there is a effect called quantum Hall effect. So this is a Hall effect. This is a measurement. This is a device measurement based on a Hall effect. If you fabricate a Hall device, if you fabricate a quantum Hall device that usually done at very high magnetic field and very at low temperature, then you will get some results. So if you analyze some results, those results will give you the peculiar properties of the graphene. So those results will not be observed in all other materials, even if you fabricate the same device. So it happens with graphene.
Okay.
Like
what kind of device? I'm sorry.
Yeah, please.
Yeah. What kind of devices do you make? Because we arrived a little late on the meeting, so we didn't hear anything.
Okay, what kind of devices? We make mostly electronic devices based on graphene. So these devices have graphene and mostly graphene field effect transistor with several contacts. You might be knowing about the Hall effect, right? Can you hear me?
Yeah.
Yes, I'm sorry.
You might be knowing the Hall effect, right? Hall effect in physics.
Yes.
Okay, so the same device, the same kind of devices.
Okay.
So for solar cells, it could be.
Yeah, for solar cells. So this is like, what I have shown is a simple photodetector device just based on graphene and semiconductor.
So that's why you are using Schottky junctions?
Yeah, Schottky junctions. So
to improve the
yeah. Schottky junction is what I have observed between the graphene and silicon carbide interface that actually I get to know from the device results. So I really don't know when I make the device whether I will get a Schottky junction or not. So when I study the device results from the current value, I got to know that I got a Schottky barrier. So the Schottky barrier is good for me, particularly for my device application. So I just use the Schottky barrier for further applications like photodetectors, solar cells, something. Yeah.
Well, one question more. Okay, well, Jesus, want to say something?
The question, the present question, it was very interesting because we know a kind of graphene because each time that when we write with a pencil in a paper, we have a kind of graphene. It was the something that was established in a paper of Novoselov in Applied Physics Letter, one of the first papers in graphene. But how we translate these graphene layers to the laboratory to start to study that they have so interesting properties? I don't know how. It's amazing.
Okay, if I understand your question correctly, then you mean how do you find the monolayer graphene and study further, right?
Yes, how we start to study the electrical properties of the graphene that we know already when we write with a pencil in a paper. We didn't know that the electrical properties of this writing are so important or so interesting, you know?
Yeah.
It's amazing to see that I make graphene if I write in a sheet of paper like that.
Yeah. Yeah, that's what I showed in one slide. For example, if you have 1 millimeter of graphite, then you will have 3 millions of graphene layers. You need to pull out of it, one out of it, and study the properties. It will be interesting. That's it. So that's why I think that's why they got the Nobel Prize.
Yes. Yes, as it was pointed out by Pablo, that this graphene is why take it with a scotch tape.
Yeah, scotch tape, yeah.
Yes, to make thicker, no, to make monolayer or something like that.
Yeah, monolayer, yeah.
Yeah, it is amazing.
Yeah.
Really amazing.
So it is the material of the future, Dharma. We need to study graphene in Mexico to be with the new technology. How do you think? Because we have concurrent technologies, for example, photonic crystal, quantum computers, that try to make a better electronic that we have now with silicon. In the future, we are going to have a graphene-based electronics. How do you feel about it?
Yeah, it would be good. Not only graphene, there are some other 2D materials have recently emerged, you know. There's 2D materials with certain band gap. So what I'm shown here is graphene doesn't have a band gap. So that's the one disadvantage. Okay. Still, you can choose some other materials with the same like properties, but graphene is of course the perfect one for certain kind of applications. And maybe you can try, you can do. It would be a good achievement.
We have transistor-based graphene right now, or something like that.
Transistor-based graphene?
Yes, transistor.
Yeah. Yes. We have like in papers, like in laboratory skills. There are a lot of devices. There are a lot of devices.
In the laboratory, no commercial ones.
Yeah, commercial. Very rare.
Yeah. Okay.
Few have come out, but not like the gadgets, like not the one that we are using.
Okay.
Well, it's have 1 hour and 20 minutes. So, if any other question? Well,
last one.
Okay.
Yeah.
How long have you been working with the graphene?
in my PhDs, I worked on graphene like in 2000, from 2012 to 2017. But after that, I changed my topic, like, but mostly based on 2D materials, but not graphene. Like almost 5 to 6 years, I have worked on graphene.
Okay. Okay, that's really interesting. Thank you so much.
Yeah, thank you.
Thank you so much, Jennifer.
Thank you.
Well,
Thank you.
We thank Dr. Dharma very much for his very interesting talk.
Thank you.
So we appreciate really your acceptance for this talk.
Thank you. So if you have any more questions about 2D materials and graphene, just feel free to, like, I'm requesting students, feel free to contact me. Hope you will all have my email ID.
Okay, yeah.
Just feel free to contact me.
Of course. Awesome.
All right, thank you so much.
Thank you. Thank you.
Okay, thank you. Okay, we're going to finish the transmission.
Thank you very much. Muchas gracias
Thank
a
you.
todos.
Thank you. Thank you, Jesus. Thank you,
Okay,
Babu.
thank you, Dharma.
Thank you. Thank you.